7 minutes. So the next speaker is Eric Wieser, or Wieser, I don't know.
Wieser, you got it right, good job.
Utensil song, which are Cambridge University Engineering Department and independent. I thought these are students of John. I'm not sure. Anyway, please, Eric, you have 25 minutes and 5 minutes for questions.
Okay, so I'm a PhD student at Cambridge University. I am one of Joan's students, and today's talk is about formalizing geometric algebra, which I'll call GA, into the language of a theorem prover such as Lean, which is an ongoing project between myself and Utensil Song. We'll talk about the value a theorem prover could provide to GA and the tools we've chosen to formalize it into. We'll then give a brief tutorial to demonstrate what using a theorem prover is like. Finally, we'll review and compare existing formalization approaches to GA. Overall, we believe that the experience of formalizing geometrically significant mathematics into the rigorous language of a theorem prover will provide us with productive tools to apply GA both effectively and correctly. So what do I need a theorem prover for? When I started with theorem provers, I'd never heard of them. So their most obvious use is for rigorously stating and proving mathematics in a machine-readable way, such that the proof can be fully verified. To make this more accessible, they typically include a proof assistant, a tool to guide the user as they're writing their proof, often via automation. Perhaps the most valuable aspect of a theorem prover is that any statement proved with it is put in a machine searchable database, where it can be easily found and reused in constructing further proofs. For these reasons and others, there are many who consider theorem provers to be the future of mathematics. Obviously, if you're attending this conference, you have plenty of ideas in the areas in which geometrical algebra can be used. It subsumes plenty of frequently used tools in mathematics, the complex numbers, the quaternions. It has applications in multiple fields, and it does all this while enabling geometric intuition. Of course, if we combine GA with theorem provers, we can now use the Cartesian product of all of these things. We can check correctness of proofs in computer graphics. We can reason geometrically about these proofs as well. It opens up a lot of areas of application. Let's think for a moment about the properties we want a formalization like this to have. If we look at Charles Gunn's course notes for his the SIGGRAPH talk, he presents a wish list for doing geometry. We take the most important of these wishes for a coordinate-free representation, compact and readable expressions, and compatibility with other simpler algebras. Adding to these, we also want to support arbitrary metrics so that we can add specializations for commonly used algebras in engineering, such as conformal geometric algebra and PGA. We want to be accessible to multiple mental models of GA, and as well as compatible with computational models used in existing software implementations. Finally, we'd like it to be interoperable with other formalized mathematics, as our stretch goal of formalizing geometric calculus would be a great deal easier if we can start on a formalization of calculus. So to summarize, if we want to fit multiple mental models, we need multiple extraction levels. We hope our tool can be used in research, in software development, and even as an introductory tool to GA. And we hope that this process will provide us with new insights into both geometric algebra and formalization. So what's Lean from our title? Lean is a platform for modeling mathematics, software, domain-specific objects, and rules. It can verify their correctness by stating and proving theorems, and you can build tools to help prove theorems, making it a metaprogramming language. It was developed at Microsoft Research in 2013, but now the development has moved to the community. To give a brief history, Lean is not the only theorem prover. There have been many over the past 40 years. Lean's youth allows it to pick the strongest features from those of the past while avoiding the weak points and to evolve rapidly. The current version is version 3, where development has been transferred from Microsoft to the community, and over the last year, there have been many releases, so it's very actively developed. And you can try it out in your browser today without installing anything. Development is continuing with Lean 4, which notably for GA applications will come with better support for domain-specific notation. Another interesting fact is that in future, it will compile directly to machine code, which makes it possible to both write efficient code and verify it in the same language. I'll give a quick summary of the design of Lean. So it breaks into 3 pieces. You want a high-level interface for writing human-readable proofs, but you also want this to be verifiable by computer. So you take the high-level proof, and you compile it down to smaller pieces of implicit proofs, and then finally you fill in the gaps of all the implicitness. And in the end, you pass your very long, very explicit proof into a very small trusted kernel. And as long as you can trust the kernel, you can trust that your proof is correct. Even if your proof isn't what you thought it was, you've still managed to prove your statement. It shares the same type theoretic foundation as Koch and Agda, which is stronger and more powerful than some of the other approaches used in other languages, but ultimately subsumes them. And if you want more details on the design of Lean, there are plenty of papers online, which I won't go into any more detail on. An important component of Lean is the mathematics library, which is a collection of structures and proven theorems that you can reuse in your own formalizations. Its goal is to be comparable to equivalent libraries in other theorem provers. It's maintained by a diverse and growing community, resulting in a diverse and growing range of formalizations within it. Unfortunately, it doesn't yet extend to the mathematics that this conference is about. And to give you a sense of scale, there are over 30,000 theorems in MATLib today, and the rate of growth is only accelerating. Both MATLib and the language itself are driven by the community, which varies from those using it, to those teaching it, to those trying to formalize the bleeding edge of modern maths. This requires collaboration between domain experts with specific formalization goals, pure mathematicians with good intuition for generality, and formalization experts with knowledge on how best to overlay software engineering principles on top of mathematical structure. Mathematicians are continuing to lay the groundwork to bring these tools to the daily work of scientists and engineers, but they're not there yet. To help close this gap, a variety of strategies are being used. Lean has worked its way into some undergraduate math teaching. They have online video and chat resources to help onboard beginners, and recently they held a week-long online conference. To make MATLib and Lean work for everyone, the trick is to provide tools at different levels of abstraction for different users. Mathematicians may want to work with generalized Clifford algebras, but engineers likely just want access to PGA or CGA. The mathematical sophistication remains under the hood and is central to the overall coherency of Lean, but isn't necessary to be understood by the engineers. If you want to learn more about Lean, their website is a great resource. And you can see plenty of applications of this tool actually being used for difficult mathematics. Particularly notable, perhaps, is a formalization of the continuum hypothesis. So enough about how Lean works. Let's give you a tour of how you use it. So we'll start with the basics. We'll define a name for the natural number 2. You'll notice that Lean allows us to use Unicode characters like that double-struck n, which makes it popular with mathematicians. Next, we'll define a function. So far, this just looks like another functional programming languages, again with some more Unicode. And if you look at this, there are 2 key parts. We have the n to n, which is the type, and the lambda a 2 times a, which is the value. This is when we move on to the theorem proving side of Lean. Here, the type is prop, and the value is a mathematical statement. If you look at this mathematical statement, you'll see that it's not true. There isn't a natural number that squares to 2, but we can make the statement anyway. What becomes interesting is we can then try and create a value of the type of that statement, which becomes a proof of that statement. And here's where we get stuck. We can't prove this statement, so we use sorry, which is construct a fake proof so I can keep working. Typically, you would make the statement and the proof at the same time. So here's a statement that for all values a, twice a is the same as a plus a. And this is actually a function that maps values to proofs of that value. And this is what a proof might look like. I'll show you more about proofs in later slides. It's frequently useful to bundle together a collection of statements into an object. For example, the concept of a mathematical group. I'll demonstrate how to model the statement that G forms a group using Lean's type classes. Lean has some built-in type classes which are used to define notation. We extend from these to provide the operators we need to state our axioms. Then we can state our proof axioms, each of which holds a proof. Looking at this through the eyes of a software engineer, type classes can be seen as a way of defining an API. Implementing this API would look something like the following, where I've sorried out all the proofs for brevity. Once we have an API, we can write proofs against it. Let's do that now. Lean has multiple paradigms for constructing proofs, the most approachable of which is its interactive tactic proving. We'll prove a trivial lemma about groups, which is shown here both as math and as Lean. The group G bit tells us we can assume G is a group. Note that an implication is just a function that maps a hypothesis into another result. Once we've stated our goal, we can enter tactic mode, and Lean pops up with a goal window telling us what we have to prove. We'll start off by naming our assumption, which changes the tactic state again, and then we can rewrite using the assumption by substituting it in. Finally, we can apply our group lemmas until Lean tells us that our goals are accomplished, and we're done. It's important to remember that Lean is generating a proof for us behind the scenes. The interactive tactics are not themselves the rigorous proof, but instructions for the Lean elaborator on how to generate such a proof. This type of proving is great if you don't already have a proof in mind, but if you've written one on paper, sometimes you just want to directly transcribe it. This is supported too. What you can do is write down all your steps, and then you can fill in how you made each step, and this will be considered a valid proof too. Lean has another mode though. Our statement was pretty trivial, and we prefer to let the prover solve this for us. To make this work, we can tell the simplifier about our group axioms and set up the same problem as before. This time though, we can knock out the entire problem with our tidy tactic. If we want to know what tidy did, we can add a question mark and it will break it down into smaller tactics to give us some understanding of what's going on. Lean is full of such automation tactics, perhaps the most notable of which is library search, which searches the entire library of mathematical theorems and sees if any of them match your goal. Just to give an example of what a longer proof can look like in Lean, here's a proof that for all integers, if you have a is less than b and b is less than a, then a must equal to b. I'm not going to walk through the whole proof, but this is showing that there are tools for structuring your proofs into steps like have and show. Many words used in a typical informal proof have corresponding tactics, such as obtain, without loss of generality, etc. So to summarize, Lean strives to be both easy to author and easy to read. It leverages the language and symbols used by mathematicians, allowing expressions, theorems, and proofs to resemble their equivalents on paper. Many find controlled natural language too restrictive to be natural, but too flexible to be predictable. By restricting its use to structuring proofs only, Lean avoids this second shortcoming. It provides an interactive environment which behaves like a multi-level game, encouraging the user to employ a divide and conquer approach, knocking out their goals one by one. Were this all it provided though, then lots of time would be wasted on precisely solving trivial goals. By also providing a tightly integrated automated theorem prover in the same language, this shortcoming of interactive provers is avoided. Mixing the two also allows avoiding purely automatic proofs which would offer no intuition to the reader. Expressing GA in a new prover is not a tedious forcing task. Existing formalizations differ significantly in their approaches. We steal Heston's metaphor here that we're putting old wine in new bottles. We hope that the tools provided by Lean will give us new ways to think about the problem than those available to previous formalizations. So let's review some approaches to defining the objects and operations of GA that others have used. Code from existing formalizations in the following slides has been translated to Lean for ease of comparison. We'll start with a formalization of GA taken from an application in Formalizing Origami that is specific to 3D Euclidean GA, since that was all that was needed. It defines the R vectors by their coordinates in some assumed basis, and the multivectors as the direct sum over the R vectors. While this definition is concise, it leads to a very tedious definition of multiplication. Any proof that needs to expand this multiplication would inherit this tediousness. It also doesn't support arbitrary dimension, arbitrary metric, or is coordinate free. So this isn't suitable for generalized formalization. The next approach we'll look at is more general and uses a tree representation of multivectors. This lends itself very nicely to recursive definitions, such as this definition of the wedge product, and they're both easy to define and write proofs about. It's worth mentioning this representation is shared with high-performance numerical GA libraries like Garamond. However, this work does not extend to the full geometric product, as it was directed only at the Grassmann-Cayley algebra with signature 0, 0n. And it's not coordinate-free, as it's storing coefficients of each basis vector. Here's yet another formalization which offers the same generality, but slightly more abstractly describes a multivector as a set of coefficients indexed by the IDs of its basis vectors. The author's gone to define the geometric product for arbitrary metrics, which means their formalisms can be used for both GGA and PGA. The only issue with this formalism is it still is based on specific coordinates, which is at odds with the representation of a vector space in the MATLib library. Stepping back from theorem proving briefly, a common definition of Clifford algebras by mathematicians is as the quotient of a tensor space by an ideal, which can be thought of as a many-to-one mapping between tensors and multivectors that preserves multiplication and addition. This approach is typically avoided in engineering applications, where GA is presented as a convenient alternative to vectors, and extra mathematical sophistication would be a hurdle. But it does offer arbitrary dimension, arbitrary metric, and is coordinate free. Unsurprisingly, this mathematical sophistication is quite straightforward to translate into the language of MATLib, a library written by sophisticated mathematicians, which results in a very succinct description of Clifford algebra. Sadly, this description doesn't actually compile today because MATLib isn't equipped to deal with some of these things. Tensor algebra was only added a couple of days ago, and the implementation of ideal isn't sufficiently general. But these things will be fixed, eventually. Straying even further into the land of mathematics, there's a more abstract way to view geometric algebra through the lens of category theory and universal properties. We saw some category theory earlier this week in the Clifford Prize talk. I'm not a category theorist though, so this is a bit too abstract for me. None of the approaches so far resemble the approach we used in the example to define a group, of starting from axioms rather than from a construction. Here, we transcribe the axioms from an archive paper by Eric Chisholm, which describes a GA as a ring with an associated scalar field, a vector space, and the familiar condition that vectors square to scalars. This approach has the nice advantage that we can build upon the type classes already in MATLib and reuse their lemmas. It also seems to fit with the philosophy of MATLib, which is helpful for consistency. A big benefit of this approach is that if we write proofs against only these axioms, they will apply to all the previous constructions. Here's an example of a proof written using this approach of axiomatization, showing the symmetric product of two vectors as a scalar. The rough outline is we rearrange the result to be a sum of squares using tools within MATLib. We invoke our axioms to obtain a proof that each square is a scalar. And then we can just throw all of these assumptions at MATLib, it'll piece them together, and it will find a solution for us. So what's next? We need to continue with our definitions of multivectors and their operators. And once we have that, we can start writing proofs. We'll start out by proving an introductory definition of a simple geometric algebra satisfies our definition, which acts both as a confirmation that our definition is accessible and acts as a learning resource for GA users who are new to theorem proving. In parallel, we can start writing out elementary lemmas and their proofs, such as identities between wedge and contraction operators of blades inverses. With these lemmas written, we can construct automated proof tactics, which apply these in sequence to simplify complicated proof terms automatically. Finally, we can state and prove theorems about objects and transformations in the often applied algebras of PGA and CGA, where there would be the most immediate value to scientists and engineers. At this point, our toolbox should be well stocked enough for others to start using it, and we hope to inspire others in the GA community to join us in formalizing their own work. Some worthwhile theorems to state and lean to test its versatility would be the algorithm for computing multivector inverses we saw in Shirakov's talk yesterday, and geometric calculus. So that's all I have. Here are a bunch of links to learn more about our work and the tools we're using. Do you have any questions?
Okay, thank you much for the nice lecture. So this is, we were waiting for long for such effort to get a computerized way to prove theorems so that it will help to reviewers to check some theorems which are false, but with this no time and machines to prove that, so it will help a lot. I recall Perti Lunesto in Cambridge in a meeting that we had something like 15 years ago. He was dreaming to bring his CLICAL to an interface with graphic interface in order to prove theorems. You know, Perti Lunesto were feared.
I think I have a quote from him somewhere in this presentation.
Because with CLICAL, he proved theorems of the community, and during the lectures, even he raised his hand, and the lecture was frightened because some equation of theorems were wrong. So John is laughing because Perti Lunesto was called the Clifford policeman. You know? So that you are doing an excellent job. So Humboldt also was involved in the last 10 years in theorem proving, so it's a good news. So even I will try to use Lean and your work to try my equations and so on. Okay, so please, there's questions of the audience.
Could you elaborate? What's the tensor algebra thing that was recently created in the past few days? What's going on with that?
So as of a couple of days ago, there is now a definition of a tensor algebra within MATLib. And so if I go back to give me a sec. If I go back to the definition using the tensor algebra, that's one fewer piece we have to wait for in order to make this definition. So if I go on this slide, nope. Right, so this tensor algebra class here was only just added to MATLib. So that means we can now make statements about tensor algebras. What isn't in there yet is this ideal class only works on commutative rings, and a tensor algebra isn't a commutative ring. It's non-commutative. Does that answer your question?
Are you collaborating on that at all, or what's
We're
your goal?
collaborating a little with the guy who put this in. Yeah, we've realized that the things we're working on are quite similar. So we've started some conversations with him, but this only happened in the last few days.
Okay. Yeah, I'm very interested. I think I'll take a look at that very soon.
Yeah.
Okay, this other question. I have a question. You know, I mean, in the past, we have witnessed efforts of people writing code for geometrical or Clifford algebra or geometric algebra computing. The one very famous is of Rafa Abramovich. I use actually Maple Clifford to compute many things in higher dimensions, beautiful, but not for theorem proving. Now I am wondering, by using Lean or extending Lean, you cast all the equations of geometric or Clifford algebra in a matrix setting and resort to all the libraries for matrix computing, which facilitates the job, or you prove your equations without leaving the geometric algebra framework or Clifford algebra framework.
So that's the idea of this axiomatization slide. You don't actually store any information about you don't even have a representation of a multivector. You just say anything is a multivector if it satisfies these properties. And then you go on to write proofs assuming those properties without ever specifying the representation. And then if you wanted, you could say later, hey, look, matrices behave like geometric algebra. I could implement them with matrices. So you could write an implementation in Lean using matrices, and you could use all your proofs in it. Or you could say, I want to write an implementation using tree representations of multivectors, and you could do that. And whichever implementation you chose, you could still apply the same proofs to it.
Okay.
Does that answer your question?
Yeah, yes. Using representation theory, in this case, you use the appropriate for geometric algebra without the need necessarily to geometric to linear matrix representation. Okay, thanks.
Exactly. And actually, this is something that happens inside MATLib itself. So they have formalizations of matrices, but they rarely use them, and they mostly use formalizations of linear operators. And then they just say that a matrix is a linear operator, and we can reuse all the proofs.
Okay, great. Just to mention, in all these packets for geometric or Clifford algebra computing, for instance, a Clifford, and even the ClickAl from Lunesto, he resort to the matrix framework for the computing. Or you know, if you download the programs for quaternions, yeah, they resort to matrices, which is the claim is that since they are ready and are efficient from the computational point of view, they use it. But I don't like this. So your answer is nice because you are exploding the representation of geometric algebra without to mix things with tensors or with linear, unless you need, for instance, you will compute eigen multivectors or pseudo inverse, whatever. You may need the power of the linear algebra based methods because there were many guesses on that. So yeah.
Indeed, and then you can always write specialized proof that works specifically on linear algebra representations of multivectors. There's always the option to throw away the generality once you have it. It's hard to add it back if you didn't start with it.
Please continue doing this because it's a great work. So there's another questions, please. All right, so let us say our friend, thank you very much for your nice talk.
Thank you.